So welcome back, everybody. And today we are going mainly to focus on the midterm, but we are going to use the first lecture to wrap up the discussion of the stability of the Hartree-Fock equations. And I also wanted to remind you quickly about the Hartree-Fock algorithm and where you can find the program which can be of use when you are finalizing the midterm. So in the slides here for this week, there is a short revisit of the Hartree-Fock algorithm. So essentially what we, and this is something which we discussed yesterday as well, we need to set up the Hartree-Fock matrix. And typically in the first iteration, we would just set these matrix elements of the unitary transformation to diagonal values equal to 1. You can initialize them with random values. That's also possible. So it's very much up to you. And the reason why this is a little bit interesting is also that when we come to many-body perturbation theory and copper cluster theory, we will have a slightly different interpretation of these coefficients. So we're going to try next week when we begin with many-body perturbation theory. We are going to link that with Hartree-Fock theory and also full configuration interaction theory. And the way you deal with these coefficients defines in a certain way the different many-body methods. So now we are solving this iteratively. In FCI calculations, we solve the full problem, and then we simply, from the diagonalization process, we got the eigenvectors, and then we had the coefficients. So what happens is that we have, at every iterative pass, we have to diagonalize the Hartree-Fock matrix. And the typical way we proceed is by making a guess. And the most standard one is to set in a diagonal value equal to 1, and that's it. And that makes it pretty easy. And this is actually one of the exercises. I mean, the second last exercise in the midterm is you setting up the Hartree-Fock matrix and finding the single particle energies by just putting these to diagonal values. And that's typically the first iteration. So then you have the first element of the Hartree-Fock calculation. So you can do that if you think of the midterm. In that second last exercise, you can do this by paper and pencil if you want to, because you don't have that many matrix elements. But then when you write the code, you can actually check your code against your paper and pencil calculations and just see that the code has the same Hartree-Fock matrix as the one you calculate with paper and pencil. And we don't have that many matrix elements either. So that's a very useful exercise. And it's already general enough if you take the helium case, when you have only 2 particles. So for the helium case, but also for beryllium, the size of this matrix is going to be the same, because we have 3 orbitals, 1s, 2s, and 3s, which means again that we have, when we take spin degeneracy, we have 6 single particle orbitals. So your Hartree-Fock matrix is always going to be a 6 by 6 matrix. So the only thing which will change when you move to beryllium is the sum over the occupied states, which we call for, which we normally call in many-body theory, we would call that the medium. So it's not a medium which you can consult for, but it's the many-body medium. And or as we would typically call this, the density of the system, because that's defined by the number of states, and then you often relate that to the density of states. So you will often see this simply being called something which reflects the density of the system. And then these sums gamma and delta run over all the single particle states, so they run over 6. And in the case of helium, this would just be 2 single particle states, because that's the ansatz you make. And then with the new eigenvalues, you can set up the Hartree-Fock potential. And with that one, you would then diagonalize. And the way you do that is simply the simplest one, because every time you diagonalize, you get new eigenvalues. And you simply compare the sum over the eigenvalues as a vector here. So this would typically be either the norm 1, or you could do the norm 2 if you prefer that double vector. And then you compare that with a given criterion which you put up for when you want to truncate your iterative process. So when you develop the program, as we mentioned yesterday, it's convenient to actually define an intermediate quantity, which is called a density matrix. And we discussed that in the beginning of the semester, because you see now that every iteration here, you need to set up this matrix or these coefficients. And you can do that with an intermediate, as an intermediate step, by simply defining this density matrix, which now runs over the density of states, the occupied states. And you can actually rewrite this as a matrix multiplication. And you will see that down in the program. So that means that you can simply rewrite your calculation of the Hartree-Fock Hamiltonian in terms of the density matrix. So density matrices in different disguises is something which you will see again and again in many-body theory. We defined that in the very beginning of the semester. And then you can pre-calculate that one in every iteration as a product of two eigenvector components C. Because every time you diagonalize, what you get out from the diagonalization are actually the eigenvectors here, which then in a component representation are given by these subscripts, which you see here, these sub-indices. So there's a simple example here, which you can take a look at. So this assumes that you have already set up the single particle data and the matrix elements. So you just have a table with matrix elements, which you look up. Or you can calculate them on the fly if you want to, because we have so few elements. So we have only 6 single particle states. And that means that the number of matrix elements we are dealing with is not that big. And then you need to define number of iterations. Here you have the first guess. So gamma in range single particle orbitals, that's all the orbitals. Same with delta. So this is actually just setting up the density matrix. And you see now we are running over the density of the system or the number of occupied states. This is n particles here. So that defines your density matrix. So this is the sum here. And that's simply the implementation of what you see here. Nothing but that. And in the first iteration, we just put that one to 1 on the diagonal and 0 else. And you see that we just define the C as the ones here. And then you set up the old energies, the new energies, max iterations. You set up the Hartree-Fock matrix for every iteration here. And now you run over alpha and beta. And you fetch the matrix elements. As you can see here, this is the interaction elements. So you simply transfer in the original basis the indices alpha, gamma, beta, and delta. So this is what fetches your matrix elements. Or you could calculate them on the fly if you want to. But if you calculate them on the fly, you need both the direct term and the exchange term. So this is very much up to you how you want to set up the basis set. And then we have, in case beta is equal to alpha, then we have the diagonal piece, which is the single particle energies, which in our case are given by the standard old-fashioned, the standard classic Bohr model for the hydrogen atom. And that's pretty simple to add. And then you simply run over this, set up the density matrix, and then a new density matrix after you've diagonalized. You now set up the single particle energies and find the coefficients or the eigenvectors by diagonalizing. And then you define a new density matrix, which is now containing the new coefficients. Then you have the new density matrix, and that goes back again up here and enters the calculation here. So this formula, which you see here, the sum Fock term, is actually just the term which we are setting up here, this term here. And then we have the single particle piece, which comes in the if tester. If beta is equal to alpha, you add the single particle to the Hamiltonian. So the only thing you can use this program, and the only thing you would need to do then is to define the single particle array of energies. And then you need to have a label which refers to these and these single particle states. And then you need to have a label here which picks the labels, which then pick the right matrix elements. And that should be it. So, and then you can compare that to the diagonalization when you do just the one particle, one hole, and see how they compare. Okay, any questions to that?
And do you
Yeah.
Single particle
Yeah.
basis?
Yeah.
You have to calculate that using the coefficients from your C, right?
Not the single particle basis, because you can assume that your single particle basis is a hydrogen-like basis. So that simplifies life. So this is a very important question which you raise, because in this case here, we have simply assumed now that that single particle operator, which we have here, originally this is given by H0. If you assume that H0 is the operator for the hydrogen-like atoms, and then you can assume that the Greek bases, the alpha and betas, are the hydrogen-like orbitals, then this has a simple analytical expression. So many people do assume that, but you could obviously use another basis, which is not necessarily diagonal for H0. So if you're using Gaussian basis sets, which is pretty common in atomic physics and molecular physics and quantum chemistry, then this is not diagonal in that basis. And then you need to evaluate it. And you need to evaluate the overlap as well in order to normalize the product. I don't know if you've been, because you're doing quantum chemistry, and probably you've touched upon Gaussian type of orbitals.
I haven't done lots of quantum chemistry.
Okay. Okay.
So,
yeah.
but I've seen.
Yeah, yeah. So here we're going to make life much easier for ourselves. And the basis set here is simply going to be diagonal, the eigenbasis of H0. And then the new basis which you get, I mean, the solution to this problem, that's going to be the eigenbasis of the Hartree-Fock Hamiltonian. And that will change. So this single particle basis, you will see when you start iterating, that these energies here, they will change. But for every iteration, they stay the same. So the only thing which changes now is this term here, the Hartree-Fock term. That's the only one which changes from iteration to iteration. Yeah.
I have a question with the analytical views is sometimes talk about the Hartree-Fock Hamiltonian for operators, and sometimes the Hartree-Fock matrix.
Yeah.
I would assume that this should be the.
This is the matrix.
This is the matrix.
Yeah, and this is the Hamiltonian, right? Or the Hamiltonian matrix.
Yeah. Okay. So you kind of use them interchange.
Yeah. I use them interchange because the operator itself, is this operator we label with an F, which contains H0 plus the two-body potential. That's the operator F, which we defined earlier. And that operator then depends obviously on the medium you're looking at. But here we are looking at the Hartree-Fock matrix elements in a given basis. And then clearly what we have here is a Hartree-Fock matrix. But often we define that sloppily as a Hartree-Fock Hamiltonian, which is now acting on this basis here. So when I put hats here, this is an operator which acts on it. But in practice, since this is discretized, this becomes a matrix times a vector. So you could still think of this as the continuous problem. But in all actual calculation, we discretize and have a finite basis.
If they have like infinite and
yeah. Then it will be, then you will be solving the continuous Schrödinger equation. But it's always discretized. And for all actual calculations, we always end up with a truncation of the infinite basis. So hopefully you can take a look at that. And the thing which is nice with this system is that you can do a lot of by hand calculation. So the first iteration, as I said, is something you can actually develop by paper and pencil. And that was the second last exercise. And then you can also check that your program is running correctly, so that in the first iteration, when you're setting up your Hartree-Fock matrix in this when HF count is equal to 1, then it should be given by the first iteration, which you then have calculated by paper and pencil, or numerically if you wish to. That's very much up to you. Okay, so one of the things I wanted to say a little bit about is the Hartree-Fock equation in second quantization. And I just wanted to add a little bit about the equations we looked at yesterday. And since I want to spend more time on the solution and discussion of the exercise, I thought of sending the derivation of Thouless theorem to next week. But the basic idea is that you can write a general Slater determinant in terms of the so-called ansatz for your vacuum state, which in this case, the C could now be your Hartree-Fock vacuum state. But it could be any Slater determinant. And this is now written out in terms of a sum over all the one particle, one hole excitation. So we are coming back to this specific expression where we exponentiate it. So this is something which is going to be important when we are going to derive copper cluster theory, that this actually is equivalent with us summing to infinite order all one particle, one hole excitations. We are going to discuss that a little bit later, but now we are simply assuming that a general Slater determinant can be written out in terms of one particle, one hole excitations, a linear combination of them acting on the original state. And what we did yesterday was to use this, and we didn't prove this expression, but we used this to look at the stability of the Hartree-Fock equations. So what we wanted to show then is that this general Slater determinant gives us the Hartree-Fock energy or something which is larger than the Hartree-Fock energy, guaranteeing then that if this expectation value of C is the Hartree-Fock energy, that is indeed a local minimum. So that was the arguments which we went along yesterday, and here is a derivation of the Thouless theorem. But I wanted more to focus on the thing which is interesting for us. So this general Slater determinant, what we started with yesterday was to show that this Slater determinant, when we calculate the expectation value, since this is not normalized, we need to divide it by the normalization term. And then we can then show that this is, with some given conditions, that this gives an expectation value which is larger than the Hartree-Fock calculation. So if you have if somebody gives you a Hartree-Fock Slater determinant for the ground state of the system, what we want is this to be a local minimum. We don't know whether this is the global minimum, but we hope that with that basis, we are getting closer and closer to the global minimum, or the minimum we want to reach. So Hartree-Fock theory guarantees only that you reach a local minimum. Whether that's a desired local minimum, that's another issue. But what we are stating now is that this Slater determinant, this general Slater determinants in terms of particle hole excitations, is something which now gives an expectation value which is larger or equal to the Hartree-Fock energy. That's the basic assumption we are making now. And then what we did was simply to expand this exponential here in terms of the different coefficients of the particle hole excitations. And since we wanted to perform the calculations to second order in the unknown coefficients, we would truncate this series at this level here. That's what we did yesterday. And by truncating that at that level, we needed then to calculate the different matrix elements. So we have a 1/2 factorial, and then we need to calculate these expectation values here. And what we did yesterday was this kind of exercise with the second quantization formalism and using Wick's theorem, and we computed the different contractions. So when we did all these contractions, what it resulted in is a matrix which now contains different terms here. And so let us wrap up the final matrix which we ended up with. So what we ended up with when we did everything here is that we could rewrite the problem here in terms of the ground state expectation value, which is our Hartree-Fock energy. We have this coefficient which comes from the normalization, because we stop the denominator. If you go back, we stop the denominator, which we have here at second order in this coefficients delta. And then we do the same thing with the numerator. So we truncate here, but that means that we also need to truncate in the denominator, so that we have the denominator to second order in these unknown coefficients and the numerator to second order in these unknown coefficients. So that's the approximation we make, because else you would just be going on and calculating higher and higher order terms. So this is an approximation, and we assume that these high order terms, which are then linked with the terms which include delta C to the power of 3 and so forth, that they can be neglected. And that means that we get this factor which you see here from the denominator. And these are the terms which we get in addition, and they are defined by this matrix element. So this is normally called, this matrix element here is a so-called one particle, one hole excitation, because we have a one particle, one hole here, and we end up with a one particle, one hole. This, on the other hand, starts with two holes and ends with two particles. So this is a two particle, two hole excitation. If we put these two particle, two hole excitations to 0, then the equations which you see here will only contain this term. That leads to a famous method in many-body physics, which is called the Tamm-Dankov approximation, or just the TDA approximation. So the TDA approximation is actually an approximation where you then want to solve this problem in terms of the unknown coefficients. So you can rewrite that as an eigenvalue problem. And I'm going to give you the derivation of this method later. And that means that you end up with a pretty simple equation which can be solved analytically by matrix inversion. We're going to see that later. So some of you may have heard about the TDA approximation, or Tamm-Dankov. Some of you may have heard about the random phase approximation, the RPA. So the RPA means looking at this problem, including the two particle, two hole excitations as well. And if you take this away, you can actually you can rewrite this in terms of a matrix inversion problem, and you can find the coefficients by just inverting a matrix. We are going to see that a little bit later when we are going to look at approximations of many-body theories. But just keep these calculations in mind, because I'm going to bring them up a little bit later. So the random phase approximation means that we would be solving this type of equation for the unknown coefficients in terms of both this one particle, one hole excitations and this two particle, two hole excitations. Because here we go from a two hole state to a two particle state. So these matrix elements represent a two particle, two hole excitation. And in the Lipkin model, which we do have these type of matrix elements. So in the exercise next week, you will actually practice on the studies of the stability of the Hartree-Fock equations. But if you now look at the equation which you have here, so now we are looking at the sum of all these indices. This is something which we can rewrite in terms of a matrix problem. So if you look at what we have here, we can now pick this term with 1 plus this delta Ci squared, and just keep that one outside. This would now be your Hartree-Fock energy, if you are on a Hartree-Fock basis. And this delta E contains now the remaining terms here. And here you have the one particle energies in the Hartree-Fock basis. So this will be your particle energy, and this is your hole energy. And this defines now this quantity delta E. And what I've done now is simply to divide again with this term here. That's the approximation to the norm, which I divide with. So then I have E0, which is my Hartree-Fock energy. And then I have this term here, delta E. And if you look closely now at delta E here, it contains a delta Ci squared. So this is the complex conjugate times the non-complex conjugate, like we have here. Now, since you have a sum over A of I, that will be the diagonal element in a matrix of a particle hole configurations. Here you have a quadruple sum, and that becomes an element in a matrix which contains also non-diagonal terms. So what I'm going to do now is simply to rewrite these guys here in terms of a matrix, which I call for M. And now you see that we have this matrix A, and then I have the matrix which now represents two particle, two hole correlations. So this element here is the Hermitian conjugate of the element here. And when I do that, I can rewrite this matrix in terms of delta E, which is simply the difference between the single particle energies for particles in whole states. So which I will have on a diagonal. And then I need to have A here, but I will also have the complex conjugate of A, or the Hermitian conjugate. So this matrix M here is now defined in terms of these matrix elements. And then I can multiply with the eigenvectors, or these coefficients delta. And then I can simply require then that if I want the condition to be satisfied, this delta E has to be larger or equal than 0. So that means that this matrix, in order for that to be the case, it needs to have eigenvalues which are 0 or larger than 0. So the matrix needs to be positive semi-definite in order for these equations to fulfill the Hartree-Fock condition on stability. Because if this vector here is going to give a low energy, then this E0 is not a local minimum. So that's the way you would reason here. And yesterday we actually went through the kind of gritty-nitty derivations of these different coefficients by just applying Wick's theorem. Now, when you do this, you know then that if we sum over the diagonal elements, so you can obviously, to find out whether the matrix is positive semi-definite, you need to diagonalize. However, diagonalization requires normally many cycles, but you have a necessary but not sufficient condition for finding out whether the matrix is positive definite. And that is to sum up all the non-diagonal elements and compare that to the sum of the non-diagonal elements. So one of the requirements then is that the sum, if you take these non-diagonal elements and sum them up, they should be larger or equal than 0. That's a sufficient, no, necessary, but not sufficient condition for the matrix to be semi-positive definite. I don't know if you remember from computational physics, when we discussed the matrices which are positive definite, and how you can actually by inspection look at the matrix and figure out at least if there is an indication that it's positive definite without having to diagonalize. So that means that you can read off the diagonal matrix elements by then punching in the values of these matrix elements and the difference between the single particle energies. So what you will typically see now is that if you have a system which has a high density of states around the Fermi level, then one particle, one hole excitations can become very important. And then this quantity here can be close to 0. So Hartree-Fock works well when you have a large gap between states below the Fermi level and above the Fermi level. So that means it works best when you have a typical closed shell system. So in nuclear physics, that would be a nucleus like oxygen-16, which has a difference between the last whole state and the first particle state of 6 mega electron volts, typically, no, 4, 5. And the matrix elements on average are something like 1 to 2 mega electron volts. So that means that this difference is larger normally than the matrix elements here on average. If you, however, have a very, very dense number of states, So if you're thinking of a harmonic oscillator, which is very wide, then the oscillator energy is very small. And then you can easily excite a hole above the Fermi level. Then Hartree-Fock breaks down. And you will see that very clearly, that the Hartree-Fock energy does not lead to a converged solution. Your iterative scheme will not converge within the number of iterations you're willing to spend. So this is a very nice condition, actually, because you can look at a given physical system. In nuclear physics, you can extract from experiments something which is called a shell gap. I don't know if you've discussed that in nuclear physics. So the shell gap, you can take that from experiment, assuming that Koopman's theorem is valid. Remember, Koopman theorem is this kind of, it's not a theorem, but it's an assumption that the Hartree-Fock basis is the same for a system with n-1 particle and n particles. And then you can interpret the Hartree-Fock solution in terms of the single particle energies as the energy difference between a system with n particles and n-1 particles, or n+1 and n particles. So if that is valid, you can calculate something which is called a shell gap in nuclear physics, which is actually the difference in binding energy between a nucleus with, say, 16 particles and 15 particles. And then you can look at this specific number and extract this quantity here, assuming that Koopman theorem is something which you can use. So it's, as I said, it's not a theorem. But then, if this is the case, and these matrix elements are not very large in absolute value, then this condition can be fulfilled. And that's quite interesting, because if you can just look at the experimental values and look at these energies, energy differences, and that can give you kind of indication of whether Hartree-Fock basis can be a good starting point or not. So this was a kind of way of wrapping up this discussion of the stability of the Hartree-Fock equations. And next week, when we move into perturbation theory, I just wanted to bring this derivation of Thouless theorem up again, because that's also useful when we move to perturbation theory, because then we're actually going to include correlations beyond the one particle, one hole type of correlations. And as we saw yesterday, Hartree-Fock theory actually zeroes out the one particle, one hole excitations. So you can think of Hartree-Fock then as a unitary transformation, which zeroes out the one particle, one hole correlations, or that block of matrix elements in the full configuration interaction approximation, where you just zero out the matrix elements which involve excitations from the ground state to a one particle, one hole state. So this is something which we're going to bring up, a Thouless theorem, next week again. And then we're going to look at many-body perturbation theory, which is our first many-body method beyond Hartree-Fock theory. And that is a way by which we can include order by order in perturbation theory, more and more complex excitations. So now we've only dealt with one particle, one hole excitations. But the system contains many more complicated types of excitations. And then the question is, how do we handle these type of excitations in a systematic way? So perturbation theory does it order by order. And the weakness there is, again, something which is related to these single particle energy differences, which we have down here. So many-body perturbation theory, actually its convergence, order by order, depends on the strength of the interaction matrix elements, and also the spacing between particle states and hole states. So if the spacing is small, perturbation theory may not converge. And we will see examples of that. But it allows you, in a systematic way, to bring in order by order more complicated correlations. So we will see that when we go to second order in perturbation theory, we are going to bring in one particle, one hole excitations, and two particle, two hole excitations. When we move to third order, we will bring in 3 particle 3-hole excitations. Fourth order, we add 4 particle 4-hole excitations, and so on. So this is a order by order approximation, which may not converge. And that's why people move to other methods like copper cluster theory, where you can sum to infinite order specific types of correlations. So these are all the methods we're going to look at now are approximations to the full configuration interaction theory, where we deal with types of excitations to either order by order in interaction, or we can sum some of them to infinite order. So coming back to this Tam-Dankov approximation, if I zero out everything here with 2 particle 2-hole, I can actually solve this eigenvalue problem analytically by matrix inversion. And we will see examples of that next week as well. So this was just to give you kind of the broader picture, and then we need to dive into the details afterwards. But this Hartree-Fock stability provides us with a kind of starting point for looking at more advanced methods. And Hartree-Fock theory is a kind, as we described in the beginning of the semester, is a kind of kitchen item in many body physics, because you would typically normally have a Hartree-Fock basis, because that zeroes out the matrix elements between the ground state and the 1 particle 1-hole excitations. So that means that in your many body theories, you can leave out specific contributions. And the hope then is obviously that your many body methods may converge with less cycles. So you can think of Hartree-Fock theory as a kind of kitchen item in all many body physics.
Could you explain a little bit more about the motivation of setting up that M matrix? Because I understand what we are analyzing, but
Yeah.
how did you have the idea of setting up the M matrix in that specific form?
So if you look at these terms which you have here, this is a quadruple sum. So you could now think of summing over particle hole excitations, right? And these particle hole excitations, which you see here, they can then be rewritten in terms of a matrix. So if you look at the individual components which you have here, so let's try to write it down and just bring this up here. Right? So let's just change a little bit, and let's try to wrap this stuff up before we move over to the solution of a project number 1, or the first midterm here. So what we have, so let me just bring this up. So when we looked at the stability of the equations, what we did then is to have this equation with H, C prime, and then we have 1 plus, and then we have the sum over A and I, and then we have a delta C AI. So this is the particle hole configuration, and this is multiplied with the Hartree-Fock ground state, which is something we can evaluate. And then we have these additional terms. So we have a term here, which is given by AI, and then we also have a delta CAI squared, and this is multiplied with epsilon A Hartree-Fock minus epsilon I Hartree-Fock. So let's suppose that we just look at this term. Let's just take that one. So we have plus here, but let's not look at that one. So this term here would simply be an A of I, and then we have a delta CAI, complex conjugate, delta CAI, and then we have this term epsilon A Hartree-Fock minus epsilon I Hartree-Fock. You can rewrite it in terms of a sum over AI and BJ. And then you have a delta C of A So we have a delta C complex conjugate, and then we have an A of I, and then we have a delta Bj, Cbj, and then we have this epsilon Hartree-Fock of A minus epsilon I Hartree-Fock. And this is multiplied with a Kronecker delta, where we have delta A, B, and delta Ij. So when we run the calculation yesterday, we found this as one of the contribution of the expectation values. Now, what you can do now, if you look at this one, you could now think of this now in terms of new indices. So you would now say that you have a particle hole configuration, config, and let's just call this a configuration I, which now contains A and I. I'm just putting uppercase letters. And then I have a new one, J, which is given by B and J, the single particle states. So that means that what I can do now is actually to rewrite this term as a sum of I and J. And then I have my single particle states here, where I now have my delta, no, not single particle states, but I have this delta of I, delta C of J. And this is now multiplied with these elements where I now have I have to keep this epsilon A, or let's write it in a different way. I'm just gonna call this for a delta epsilon of I, J. Okay? And this delta epsilon of Ij is now going to be given by epsilon A Hartree-Fock minus epsilon I Hartree-Fock. And then I have a delta I AB, and then I have a delta Ij here. So this is just going to be a diagonal matrix element. So when you look at this one, the way you can rewrite this is in terms of the vector C here, delta C, multiplied. So this sum here actually defines a matrix. And then I would have the different matrix element here. And each one of them would correspond to a specific particle hole configuration. So I would have a delta epsilon 1, 1. I would have a delta epsilon 2, 2, etc. all the way down here to the number of particle hole excitations which I have available. And this is then multiplied again with a vector delta of C. So you can, since we have this quadruple sum here, you would typically rewrite each one of these in terms of a specific configuration, a particle hole configuration. And this particle hole configurations, this gives then a matrix element, which is now simply given by the difference between epsilon A and epsilon I. And then I have these Kronecker deltas, which then also translates into us being able to rewrite this in terms of these specific configurations. If you look at the next term, which we have, then we have a term here, which goes like a sum over AI and a sum over Bj. And then I have a delta of C complex conjugate. And then I have an AI. And then I have a delta of C of Bj. These are the coefficients. And then I have the matrix element, which in this specific case was now given by a matrix element, which I called A of AI and Bj. And that matrix element, AI and Bj, was the same as minus. And then I have my A of I, of V, of B of J. And then if I put these indices here, I can actually, this indices I and J here. You see now that I can actually rewrite this as a matrix A of I of J, a matrix element. And that means that I can now rewrite this sum in terms of I times J a delta C of I, a delta C of J, multiplied with a matrix Aij. And this is something which I formally can rewrite as this vector delta C multiplied with the matrix A and multiplied with the vector delta C. Did that help a little bit? So this is the way you often think, because we have broken things down in terms of indices. But then you could think of every such index as a particle hole configuration, and you can give that its own label. And you can do the same with the other matrix elements, which we then define non-diagonal matrix elements of two particle, two hole excitations. And with that, you can rewrite this delta E in terms of a matrix. So what you would have then is 1/2, and then you have these vectors. You were going to have a delta C and delta C here when you write out the term B as well. And then you're going to have multiplied with a matrix of this delta epsilon plus A. And then you're going to have this matrix elements B complex conjugate, and then you're going to have a delta epsilon plus A complex conjugate. And then multiplied with this vector delta of C and delta of C complex conjugate. Because we have to look again at the equations here, because there will be terms which involve delta C in slightly different ways.
Why would the A be? Because now it looks to me like A is also diagonal, which is strange.
A
Then
is,
delta E up there, I agree with the first one you did.
Yeah,
That's
yeah,
diagonal.
yeah.
But this A matrix.
yeah, but the first part doesn't have a factor of 1/2 here. So what I'm doing now is to because if I go back, let me just go back to the equations which we have, and let me just show them. Let's go back to them. So if you look at the equations here, this first term doesn't have an A here,
Yeah.
a factor of 1/2. These two have a factor of 1/2.
Yeah. But,
So what I'm doing now, I'm splitting this in two terms.
yeah, but my question might formulate it
Yeah.
that you go to block matrix form.
Yeah, yeah,
And inside the delta E block,
yeah,
that is actually diagonal.
yeah.
But the A
Is not
is
diagonal.
not diagonal.
Is not diagonal,
But in
right?
the block.
Yeah.
When you wrote it, it only
Oh, yeah.
contributes to the diagonal.
Yeah,
block.
yeah.
Okay. That
Yeah,
makes
because
sense.
this is not this block. This is a block now which contains diagonal elements
Mhm.
plus non-diagonal
Yes,
ones.
okay.
And the same with B is a non-diagonal block.
Mm.
And the fact that the reason why I did this, because this A and A complex conjugate, they are the same, but I'm simply rewriting because here I have actually interchange, because here I have a delta A, there are no complex conjugation here, whereas I have them here. So what I'm doing now is simply to use the fact that I have 1/2 here, 1/2 here, and I want to bake in the factor of 1/2. So then I just rewrite the B's like this, and then I multiply them with the coefficients here. And since this other term here doesn't have the factor of 1/2, what I'm simply doing now is I'm just duplicating that one here and here. And then I have the factor of 1/2 in front. That's the main reason. And then I can actually rewrite it in terms of this specific matrix here. And what we are going to see next week is that we're going to put the B's to 0. And then we have a problem which we can end up being able to solve analytically by matrix inversion. And that's pretty nice. And then we move over to many-body perturbation theory. But take a look at these expressions, because we will practice a little bit with this with the Lipkin model. And in the Lipkin model, we have very simple expression for the matrix elements. And then depending on the values of the single particle energies and the matrix elements, we can get stable solutions or non-stable solutions. So I'm gonna stop the recording here. And I will upload this one, and then I thought that we can take a small break now. And then we spend the rest of the time discussing the midterm. If that's okay with everybody. So I don't want to bring up, I don't want to bring up a new topic when you guys are struggling with midterm.
That's right.
That's
very
the-
high.
No, no, it's,
Oh,